Okay, so a dipole moment is just a dipole. I don't know why they call it a moment. Okay, but it is really just a dipole. And so here, what we're looking at is we have, for example, oxygen and hydrogen. There is a bond dipole. The bond dipole is that. And we have a bond dipole that does that. And the net dipole points that away. So far, so good? Okay. So that's what a dipole is. Do you want to know how to figure out how to draw a net dipole moment? Are you interested in that? Okay. So back on page 24. Yes. You might have to, yeah. Okay. Yeah. So how many people have done vectors in physics? Okay, so you don't know all about it. These are just easy ones. Okay, there's nothing particularly difficult about it. Basically, what it comes down to is often vectors are used in terms of forces. Okay, so if you have a 10 Newton force pushing to the right and another 10 Newton force pushing to the right, the net force is 10 to the right and 10 to the right, which equals 20 to the right. Yes? Okay, so this is in one dimension, all right? We could have things going to the left, so this is to the left, 10 newtons to the left, 10 newtons to the left gives us 20 newtons to the left, all right? What if we have 10 newtons to the left and 10 newtons to the right? What do we get? Get 0 because they cancel out, right? The vectors cancel. And if we have 20 pushing right and 10 pushing left, this portion cancels out, right? 10 newtons cancels out. And so you are left with 10 newtons to the right. Is good? Okay, so that's in 2 dimensions. You can practice doing these if you want to. What you would have to do is you would have to, say if you had this one here, you would have to actually line them up, right? You would have to say, instead of having this here, you would move it over here. So you can say, okay, this, your net dipole would then be this. Is good? Okay, and then this one here, you would have to say, I got this, and I'm going to take this one, and I'm going to move it over here. So my net vector would be, yes? Okay. And one thing I want you to notice, we have a tail, and we have a head. Yes? So I want you to think about adding vectors like being somewhere you could walk. Okay? If I walk forward like this. I don't want to move this one so it's over here. Because if I if I start here and I walk, I would have to teleport back to here and then walk that way. Yes? I don't know why I drew it going the wrong way. Why did I draw it going the wrong way? I don't know. Anyway, not a good example. It would have been better with this one. I would not want to draw my other arrow here, right? Or what would I not want to do? Hold on. I would not want to have like this and then like this. I cannot add them like that because one's going one way and one's going the other. Never mind, we're just going to keep going. It'll make more sense as we go along. Okay, so if I have two vectors and I'm now in 2 dimensions, so some are going up and down, some are going left and right. We think of it like walking. If I start at point A and I go to point B, if I want to add the 2 vectors, I have to go from A to B, and then I have to go from B to C. Okay, so I need to be able to walk along the entire path. Adding the vector just means doing it as the crow flies rather than doing it in an up and across fashion. So if I add them up, adding them up means I need to travel from A to C, but I just do it in the most efficient way possible, which is on the diagonal. And that gives me what they call a resultant. Okay? So I need to go from A to C. Now it is possible for me to take these 2 arrows and attach them in a different way. I could put the sideways arrow first. I could go from A to D. And then I could go from D to C. The letters are just arbitrary, okay? But the deal is with this one, I started at A and I finished at C, and I would be able to walk in that direction without having to teleport anywhere, okay? And so my resultant would be the diagonal from there to there. So if you had a dipole that pointed this way and this way, the net dipole would be like that, okay? What if you accidentally connect the head of an arrow to the head of another arrow? Well, if you were to walk along here, you'd be like walk. So you'd go from X to Y. Can we travel from Y to Z with the arrow the way it is? No, we cannot. We would have to teleport. And then we'd have to walk. So you can't do it, okay? Same thing, if you connect tail to tail, you would go maybe from W to X, walk. Uh-oh. Now I would have to teleport back to W and walk over to Z. So we cannot do that, okay? Now, what happens if you draw the resultant arrow in the wrong direction? So this is the wrong direction. This is wrong. Okay, if we start here, this is our start, right? We walk. This is our finish. We cannot then say our net walk is from the finish to the start. We want to go from the start to the finish, not from the finish to the start. So this would be our net, okay? So if we had these 2 vectors here, we can either start with this one, we'll call this A, we'll call this B. We can either start with A and then continue on with B, or we can start with B and continue on with A. But you'll notice what is the same about both of those? What did I just do with my pen there? There we go. Okay. I'm starting here and I'm finishing here. The resultant is the same. So if I had a dipole moment that pointed, if I had a bond dipole and another bond dipole, whoops, did I do that wrong? Yeah. Another bond dipole. The sum of those, my net dipole for the molecule would point that way, like that. Okay, I don't put two tails together. I don't put two heads together. I don't go around in a circle because I need to start and I need to finish. No matter whether I do it in a two-part step or in a one shorter diagonal line. Now, do you feel like you would like a little practice doing that? Nobody said yes. Would anyone like a little practice doing that? No. Yes? Okay, take 5 minutes. 5 minutes practice. 5 minutes. Yep. 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 Exactly. All right. Okay. There's no idea. Yeah, no, you're not breaking into rules. You're perfect. Right? You're not. You haven't connected your into your tail. You've not like put your arrow going the wrong way. You're good. Okay. Like flip them? No. You cannot flip an arrow. If an arrow is pointing in a certain direction, that's the direction it's pointing. Okay? I swear on my Okay, that's one we don't have it. You don't have this arrow. Cannot change the direction of the arrow. There you go. I get it. I see it. All right, so that is then going to take you into and I don't know if any of you went over this last day, but what you can see is that if you look at the electronegativities of elements, and if you had to draw the net dipole moment for this thing, you would say you might just be able to look at it and go, that's an upward arrow. Okay, and that's the net dipole moment. You don't have to do the vector thing if it's obvious. Okay, but so this one would obviously be like that, but you could go, I've got one arrow going up and to the right, and then I've got another arrow going up and to the left, which gives me my net dipole as up. Yes, yes? Maybe I'll do my net in red. So like I said, you don't have to show this. You can just say, I can see that. But if you find it helpful, you can do this. And this is on page 29, okay? Now let's take a look at a couple other examples. And it shows the whole process here. La, 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 la. Still on page 29. Oh my gosh, this goes into horrible detail. Now we have SF2. And if you draw your Lewis structure, it looks like this. And I got a lot of people asking me about the bond angle on something like this. We are now on page 32. So this is SF2. What is this bond angle? That is not 180. Because Lewis structures don't show you actual bond angles. That's a bent. That is bent. Because what you have to do is you have to say, how many electron domains do I have? I have 1, 2, 3, 4 electron domains. And if I have 4 electron domains, my basic shape, my electron domain shape is what? Tetrahedral. Which means that if I've got 2 lone pairs on it, then it is bent. So the bond angle there, even though it looks like 180 in the Lewis structure, right, because we draw everything top, bottom, side, side, this is actually somewhat less than 109.5. Okay, but it's not represented well in the Lewis structure. But you can see if they've drawn it like this, it is closer to the truth. It's still two-dimensional, right? But this is closer to the truth. You would have one of these going backwards and one of them coming forwards. Okay, but it's tetrahedral and it is bent, and that is 109.5. So you look at this thing and you say, I have sulfur, which has an electronegativity of 2.6. We know that sulfur is going to, even if you weren't given values, What do you know about fluorine and its electronegativity? Fluorine is the most, more than anybody. So our dipole moment is always going to point towards fluorine. And if you wanted to say, what is my net dipole moment, you might just look at it and say, it must be which direction? Down. But if you're like, I don't see the direction, you could say, I'm going to draw arrow number 1. And I'm going to connect that to arrow number 2, which goes down and to the right. And that gives me my net dipole, which goes that way. Is good? Okay, let's see what else we've got here. CO2, this one's pretty straightforward. Who's more electronegative? Oh, by the way, why is this one linear and the other one wasn't? There's no lone pairs, right? How many electron domains on carbon? 2 electron domains. And so actually the Lewis structure does a good job of this one, but it often doesn't. So this one would be 180 degrees. And what's the hybridization of that carbon? This carbon is sp, because I've got 2 electron domains. Okay. Who is more electronegative, carbon or oxygen? Oxygen. So we go, okay, I've got that and I've got that. What would be my net dipole? 0, because they cancel out. Okay, let's keep going here. This is now on page 33. Now we don't have symmetry. What keeps this molecule from being symmetric? It's got a carbon, it's got double bonds over here, it's got double bonds over here, but what's different about each side? We have different atoms. If the atoms on the outside of the central atom are different from each other, you will probably end up with a polar molecule. Yes, because they'll have different electronegativities. So here's carbon. Carbon's 2.5. Sulfur is 2.6. I would not expect you to know that. If they wanted you to do a solution like that with sulfur, they would probably give you a table of electronegativities, because sulfur is not one of the Fonch ones, and it's not like in a super trend. Although I suppose you could say it's further down the periodic table than oxygen, so it would pull less than oxygen for sure. But I wouldn't know exactly what it was compared to carbon unless I looked up the exact value, okay? So, but we definitely know that oxygen is more electronegative, so you'll get that bond dipole. You get a little teeny tiny dipole, because they're virtually the same. That's almost a nonpolar bond, yes? Okay, and so if you then add those two up, you get your net vector, which is like that. That's your net dipole.
So can we just draw an arrow?
So you can just draw an arrow going this way. And the size really is like neither here nor there. Okay, you're not being great. You won't ever be graded on like, how well did I draw the size of that arrow? Okay, no. Okay, here's the one that sometimes messes people up, because they look at this and they're like, that does not look symmetrical to me because it's got 2 things on the left and 1 thing on the right. Couple ways to think about it. Number 1, if you put, I don't know, say like a hoop, a metal ring in the middle, and you attach 3 ropes to it, 1, 2, 3, and the fluorines were people with all the same strength, and they all pulled on the rope, which direction would the ring go? Or would it move anywhere? It would not move anywhere. So if you can visualize that, you can tell that this thing does not have a dipole moment. If you can visualize, here's this thing, these guys are all pulling with the same strength, and you can think about it in that way. If I had ropes here, it wouldn't move. And if it wouldn't move, then everything cancels out. You can also draw your net dipole. So we're going to start with this one. And then I'm going to do this one. And remember, I have to go like this. And then I have this one. And guess what? I ended up exactly where I started. So what's my net dipole? 0. If you end up where you start, your net dipole is 0. So that's why something like this is nonpolar. And it's also why if you have a 5 domain, 1, 2, 3, a lot of people would look at that and say, oh, that's asymmetrical, so it must be polar. Except that what you really have, this structure is really this structure, yes? Yeah? Because it's just like, but it's tilted like into and out of the board, yes? And then the up and down is the same. And then you have 3 things sticking out in the middle, all the same. I don't know that number. Okay. You have 3 things sticking out in 120 degrees, and so those are all pulling with the same strength. So this is actually perfectly symmetrical. And so it is nonpolar. Is good? Okay. Any other exciting ones? Ooh, what would you say, polar or nonpolar, just at a glance? Polar. And if you just had to draw a dipole moment without knowing anything else about it, which way do you think it would point? Straight up? Over to this way, yeah? I didn't do it quite right. There we go. That's better, kind of. Do we like that? Okay, and if you had to, you could say, okay, I have a strong dipole here, because fluorine's the most electronegative. I have a strong dipole here, and I have a decent dipole here, but it is certainly weaker. I'm going to take this one. I'm going to add this one. And then I'm going to add this one. Yeah? So now, here's my start. Here's my finish. So which direction should it go? Exactly the way that we thought it should. Be careful that when you're drawing your resultant that you don't just complete the circle and just keep going around in a circle. You don't want your arrows to ever, like, your original arrows can go around in a circle and cancel each other out and give you 0, but you don't want your resultant arrow to just continue the circle in the same direction. It has to go from start to finish. Okay? But, like I said, did you need to do this whole process to tell which direction the net dipole was? Probably not. You could probably just be like, oh, it goes that way, right? Any other exciting ones? Bond polarity, and then the shape gives you molecular polarity. So are any of the bonds polar? If the answer is no, then the molecule will not be polar. So that's why carbon, which is approximately the same as hydrogen, anytime you have carbon and hydrogen, huh?
That's okay.
Hi.
You're in a deep lesson.
Oh, no, it's okay.
Well, we have a couple students that we didn't survey to be done, but I don't want to go through that.
Oh, yeah, no. Yeah, no. Yeah, okay. I'm like, if it was my grade 9s, they could come in, but you guys don't need to take a survey. So we have carbon is approximately the same as hydrogen, right? You remember Flanch? Fluorine is the most, oxygen's next, nitrogen's next. and then we have carbon, and then that's approximately the same as hydrogen. So any of our hydrocarbon chains will be nonpolar because none of the bonds are polar. So the molecule will be nonpolar. Yes?
Is that the only basis of more that?
No, I mean, you could, let's just take a quick look at this one. This one had this little table here. So if you had, according to this table, nitrogen and chlorine are the same. Okay? Now, is this table perfect? No. You go to any textbook and you will find electronegativity values that are slightly different from one another. That's because electronegativity depends on who you are bonded to, and they have to measure it in context. What is nitrogen like when it's compared with chlorine? What's nitrogen like when it's compared to hydrogen? They have to do a whole bunch of measurements, and then they kind of take the average. It's a relative value, yeah? So saying that nitrogen and chlorine are exactly the same would be a stretch. Saying that they're really close and a bond between them would be nonpolar would be okay, because nonpolar, the difference, if you have a difference in electronegativity between 0 to 0.4, that is a nonpolar bond. Is good? Yes. Krypton and xenon, they can bond. Do you remember you sometimes get the like Kr, F, F, F?
Why are we bonding krypton?
Because you can, because it's so big that its valence shell just kind of has extra room.
Okay.
It used to be so much nicer when I could say, there are unfilled D shells. But no, that's not why. Just when they get big enough, right? And you'll notice when we did the expanded octets, you would sometimes see xenon and krypton having things bonded to them. It's kind of a weird situation. They don't really happen much in nature, but you can make them happen, okay? Now, if you have atoms that are symmetrically distributed, so that would be any of your trigonal planar, tetrahedral, like anything that doesn't have lone pairs. Okay, any of your basic shapes that have no lone pairs, those are all nonpolars. So this would be all the basic shapes, no lone pairs. So if you can answer that yes to that, then you have to say to yourself, are all the outside atoms the same? If they are the same, then the molecule is not polar because everything's symmetrical and all the atoms are the same. If you have different atoms, then you're going to have a polar molecule because it'll just be, different things on this side and different things on that side. And so they'll have different poles on the electrons. And obviously, if you have asymmetric distribution, this is usually when you have lone pairs. It's going to be a polar molecule. Okay? Not always, because there's some exceptions to that. Because, think about it. If you have X and you've got a lone pair up here and you've got a lone pair here and you've got fluorine, 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 is that polar or non-polar? It's nonpolar. So you cannot just say, oh, if I have lone pairs, if I have symmetric lone pairs, one on the top and one on the bottom, and then the little tutu around the middle is just normal, then, yeah? Okay. Anyway, here we have ozone. What can you say about the polarity of ozone? Here's our resonance structures. Polar or non-polar? Is it really like this? Or is it really like this? It's really like this. And what is the difference in electronegativity between oxygen and oxygen? Difference in electronegativity between oxygen and oxygen is 0. So that is a nonpolar.
But wouldn't they still have like extra bonding that's higher? Like if it forms a resonance, if they're still like non-bonding.
Oh, I think you're right. So you would have to look at, these are our formal charges. And both of them, the formal charges give you positive. I don't think you're going to get that on the AP exam. I don't think so. I'm not going to give it to you on your test either.
So it is polar.
Oh, this one says it's a nonpolar molecule, but I don't know. Now I'm feeling conflicted about it. You've made me feel conflicted about it. So let's just say it's not going to be on your test, and I would bet money that it will not be on AP either. Okay? I know that's an unsatisfactory answer. I know you're looking at me like, what the hell? Yeah. Go ask your professor at university. Be like, ozone, explain it to me. And then you can come back and explain it to me. Anything useful here? No, these are all the same. Blah, 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 yada, yada, yada. CH4, are we all okay with tetrahedral things with all the same atoms all being nonpolar? Tetrahedral is symmetrical, so it's nonpolar, we're good? Okay. All right, do we have any other questions? I think we've talked about polarity enough. Any other questions on anything? So it can be a concept, a test, yes? A non-directional bond means that I came across this morning too, didn't really like it. So we have, if I have CO, it's only in this direction, yes? If I have Na plus and Cl minus, it's only in this direction. But metallic bonding, I've got my cations and I have my electrons. Those electrons move. So this electron might be here and might be attracted to this, to the one on the right. It could be attracted to the one on the left. It's attracted to this one. It's attracted to this one. But later it moves down here and now it's attracted in this direction and this direction. So that would be non-directional. I don't think that's a word that's going to come up, but does not have a specific direction, okay? And I think really only metallic bonds are non-directional. Yes. Yep. 10F. Okay. Where did I put it? Oh, it's in here. Is it? No. Where did it go? Oh, there we go. Okay. Free response bonding number 10F. Okay, so we've got ethene during the dehydration process. C2H4 and the unreacted C2H5OH pass through the tube into the water. So during the dehydration process, they pass through the tube and into the water. So we had ethene, C2H4, and we also have unreacted ethanol. So coming through this little tube here, what they're telling us is in this little tube, we have both ethene and we have C2H5OH. Both of those are in this little tube. And both of them end up going do-do-do-do-do-do-do-do-do, and then they end up in the water. Yes? And they're both gaseous. And C2H4 was collected as a gas. So it once we're in the water, we end up with ethene up here. And no ethanol. What happened to the ethanol? Both the ethene and the ethanol were in the little tube. They both bubbled into the water. The ethene ended up at the top, but the ethanol didn't. Why? I think that's what the question's asking. Let's go make sure. Explain this observation in terms of the intermolecular forces between water and each of the two gases. What happened to the ethanol between here and here? And you have already drawn some Lewis structures. Yes? Where did the ethanol go? Did it disappear? Yes.
Oh,
It got hydrogen bonded to the water. Yes, it's passing through the water. And as it's passing through the water, this little lone pair says, oh, look, a lovely little hydrogen. Yes, and these guys will move closer to each other and they will H bond. So you'll get H bonding between the ethanol and the water, and the ethanol will then dissolve into the water. But what about the ethene? Will the ethene dissolve into the water? No, because ethene is nonpolar. Would water rather stay with water or ethanol, or would it rather pair up with somebody who's nonpolar? What's more attractive to water?
that's worse.
The other water molecules or the ethanol are attractive to water, and it looks at the nonpolar ethene and says, not nice, right? It's like the ethanol and the water are magnets, yes? And the ethene is a ping pong ball. Yes, magnets will stick to magnets, and the ping pong ball will just keep going. Okay, that's a good question. Any other questions on anything?
Nice.
9C?
Yeah, like right there.
Okay, for each compound, list all the intermolecular forces present. So, okay, so we have LDFs in both of them. Why? Because you always have them. And what do we have in this guy here? We have an O bonded to an H, so we can get H bonds. And anytime you have H bonds, you also have dipole-dipole. Anytime you have H bonds, you have dipole-dipole. Anytime you have H bonds, you have dipole-dipole. Just go with it. It doesn't make me really happy either, but that's what, isn't that what the answer key says?
Yeah.
Yes. And that's what AP says is in the answer key. So I'm like, okay, every time you have H bonds, you also have dipole-dipole. Just go with it. I don't really understand it either. Okay? I would think that the H bonds would supersede that, but what I'm thinking is that maybe it's just like this part of the molecule is more polar, and so it doesn't quite form that. It doesn't, I don't know.
So if there's dipole-dipole, there isn't necessarily.
Pardon me? Okay. Now, in compound number 2, we also have, what do we have? H bonds. And we also have dipole-dipole. Yes? No, you can have dipole-dipole without having H bonds. But every time you have H bonds, you will also have dipole-dipole. Okay? Other questions? Yes? For number 6? No, it doesn't. I mean, you could draw it like that. Usually when we draw, it's just sort of standard practice to draw it C-O-O-H, but it doesn't have to be. Okay, so yeah, that's fine. Yes?
And more bonding and IMFs.
Yep.
We go to question 44.
44?
Yeah.
So more.
Yep, this is more bonding in IMFs. Which of the following has a zero dipole moment? Well, obviously HCN doesn't. It doesn't matter what your actual Lewis structure is like. Your skeleton structure tells you polar, okay?
But we draw the little structure for SO2.
How do you draw the structure for SO2? You say S has 6 electrons. O has 6 electrons times 2 is 12, so we have in total 18 electrons. So you say, okay, I got S, I got O, and I got 2, 4, 6, 8, 10, 12, 14, 16, 18, 20 electrons. So I'm going to get rid of this pair, and I'm going to take this pair and bring it in, so that now I have a double bond on here. Yes? You with me so far? So you draw the Lewis structure the way you would draw any Lewis structure, follow all the steps, right? And then you would say, okay, I got this thing, and it has 1, 2, 3 electron domains. So the electron domain shape is trigonal planar, and this would be bent. And since it is bent, we know that it is asymmetrical. And so it's polar. Same for N, if NO2. If you were to draw NO2, you would end up with an asymmetrical structure. Okay? Now, PF5. Polar or non-polar? Non-polar. Remember, that's a little circle, and each of these bonds here, those are all 120 degrees, even though they look different because, you know, we're trying to draw it on a flat piece of paper.
So then PF5 was how that?
PF5 is non-polar, has no net dipole. Yes.
The electrons are on L2.
Uh-huh.
So
Pardon me?
It's only 17.
NO2. Oh, okay. NO2. NO2 is one of those weird ones where it has only 17 electrons, and we haven't really done much with those. NO. I wish it would just draw a dot without making a line. Okay. So we have 5 and 12 is 17. So we say, okay, I'm going to get rid of, and I'm only allowed to have, and I have 20 electrons over here. So I need to get rid of 3 electrons from my central atom. Blech. 1, 2, 3. Ugh. That's like one of the only if you have an odd number of electrons are you allowed to have a single electron on its own. Okay? The exception to every rule, right? There's always an exception to every rule. Then you look at this and you say, well, that leaves nitrogen right now with only 2, 4, 5 electrons. We can give it 7. Right? By double bonding here. Okay? And you can look at the formal charges if you want to say, would it be more stable to have that single electron on an oxygen, or would it be more stable to have that single electron on nitrogen? Nitrogen is less electronegative, so it's better for it to be electron deficient than oxygen. Oxygen is more electronegative, so it will not be as likely to be electron deficient. Okay? And yeah, nitrogen only has 7, but that's all we can do with an odd number of electrons. We cannot satisfy everybody. Okay? But you still have asymmetry. Yes, you've still got 1, 2, 3 electron domains, even though you've only got 1 electron and the geometry might be a little bit, I don't know what the bond angles would be. They'd be a little bit weird. Yes? But they haven't asked you that, so that's a good thing. Yeah. Other questions? Huh? No, you do not get anything on the test other than your pink book. Pink booklet. And quite frankly, next year, you should be able to do it with just the front page and the back page.
Oh, hell.
Front page, back page. All this stuff in the middle?
Hold on.
You don't get any of the stuff in the middle on the AP exam. You need to either remember it or they will just tell you. Often what they will do is they'll be like aluminum sulfate, Al2SO43, right? Because they're like, you're a chemist, you should know how to write chemical formulas. So they'll often take it as a given that you can do that. Okay? So it's not going to be a huge deal that you don't get a chart of common ions. It will also be not a huge deal that you don't get a solubility chart, because either you're going with things that you're like, oh, it forms a precipitate. But this one has an alkali metal in it, so it must be the other one that's the precipitate, right? So it'll be logical, it'll be not too bad. Yes? Other questions? How many people have finished all the reviews? Finished all of it? No, okay. Would you like the rest of class, however much that is, 15, to work on them? Go.
More.